Hello, and welcome to Mesh Analysis. This lecture is about how to analyze a circuit that has different active and passive components. So far, we've studied circuits with a source and a network of passive elements such as resistors, inductors, capacitors, etc. Now we want to see how to study circuits that are a little more complicated because they have a combination of passive elements and active elements. Active elements in this particular case are going to be sources of voltage or current. So the objectives are to conceptualize the differences between the independent and dependent sources for different networks, be able to convert between them. So how to take a voltage source to a current source and from a current source to a voltage source. We want to be able to do the application of meshes to study the performance of the circuit. And next time we're going to study the another approach, which is going to be the nodal analysis, which is applying Kirchhoff's law. So if you remember, we have independent sources, and this is true for DC and AC, such that in DC you have this particular case where you can have a voltage source like a battery or some source of potential that it will give you a set amount of voltage. Whereas in AC circuits, you have this sign or this symbol for the voltage source through your circuit. So these two are voltage sources, except for one is for DC and the other one is for alternating current. Now, depending on the book or the drawing or whichever source you're following, the current sources are very similar, except for this one in our book, using italic, is for DC, and this current source using bold or capital I is for AC. So obviously this is going to be varying in time because it's a wave. These are independent sources. Each circuit will have a type of source, and depending on the source, will have performance. The dependent sources, on the other hand, are sources that are computed using a set of passive elements. So for instance, if we have a resistor and we have an independent source over here of voltage, say AC, once it goes through the resistor, then there's going to be a voltage drop, which if the circuit is designed correctly, this voltage source is going to be a constant. So another way to compute or to express dependent sources is a voltage with a constant, could be less than 1, for instance, so a percentage. That is going to be, this is going to be a percentage of the original independent source. But this one is going to be a dependent source because it depends on the value of the resistor. Same thing for current. We know that in parallel circuits, current is dependent on the passive elements. So if we have a resistor, then the scaling factor is going to be the passive element. So these two are dependent sources, and what makes the source dependent is that it needs a passive element to scale down the voltage. If you remember from DC circuits, there's a fashion, there's a method, there's a way to compute conversion, or there's a way to get a conversion of a network in series to a network in parallel. And in that particular case, we saw is that if you have a voltage source, in that case was AC, sorry, in that case was DC, but now we're going to talk about AC, which is the same thing. The only thing changing here is the source. And if you have a load connected in series to the load, you can convert this network to this network on the right by computing Ohm's law with the impedance. And in other words, you can transfer a voltage source in series with the load to a current source in parallel with the load. And we saw that in DC circuits, for AC circuits is the same, except for the voltage source is going to be in AC, it's a wave, and instead of the resistor of the load, we're going to have the impedance. So a voltage source in series with the load can be converted into a current source with the load in parallel. So if we want to see an example, here we have the case where we want to convert this voltage source to a current source. So we know that since the voltage source is in series with a load, the first thing we have to do is find this impedance, which is a resistor and inductor in series. So we're going to have to do square root of R squared times XL squared. This total impedance will let us compute the current using A equals IZ. When we compute the current, like so, we're going to be able to find the source, which is this current. And then we simply place the load in parallel with the current, like so. So why do you want to do this? If at first we have a source in voltage with 0 degrees phase or lagging, but now we have a current source with phase change or with a certain amount of wave lagging. Why do we want to do this? Well, sometimes you want to do this exactly because you want to see how is the performance of your circuit in terms of the current. And you can see that since this is similar characterization, you can see that your circuit is going to be performing in a lagging fashion at 53.13 degrees. So this is very useful because when you need to characterize your circuit for design purposes or for application purposes, you can find what is the performance given the current source. Another application or another reason why you want to do this sometimes is because if you have other things going on here after the point A and A prime, other circuits connected to this particular part, it's important to be able to take, instead of the voltage, the current, because you know you have Ohm's law, which voltage is connected to current. So you might be wanting to use the current instead to continue your computations. Okay, so this is just a tool for you to be able to characterize your circuit much better. Now, one thing that we want to talk about is mesh analysis, because when circuits are a little more complicated, involving more independent sources, so notice that in this particular circuit, we have 2 voltage sources and they are both of them AC. So the regular Ohm's law and regular methods are not very useful because now we have 2 independent sources. So the circuit behaves in a certain fashion for this loop, and then there's another contribution for this loop. So mesh analysis is very useful for this type of loops when you have independent sources. So the first thing, if you remember from DC, is that you want to create the first mesh loop. And in this particular case, we decided to go clockwise. As a rule of thumb, you should go always clockwise. And the way you choose the polarity is up to you, but you have to be consistent. So it does not matter what sign you put. If you remember, if you use a multimeter and place the probes at different places of the circuit, if you have a negative sign, it's because the polarity is incorrect. So you just simply switch the probe side and measure the positive part. So the potential part is the difference is the important part. The sign is not as important because it just tells you the direction of the current. But you need to assign the initial convention as you please. So as a rule of thumb, you would put the first loop with negative close to the ground. So you're gonna have negative and then positive. And here you can do whichever you want because it's a load. So since it's a combination of circuits, obviously there's gonna be one that's gonna be going backwards given the magnitude of the current. So in this example we said plus here and negative here, and this is because this negative is going to be connected to a positive here and a positive here. So let's say positive and negative, and in this case we go for the second loop and we say, okay, the source is going to be negative connected to this ground, positive, and then we're going to say negative, positive, and then this positive connected to this negative and positive. So notice how the loads are connecting negative with positive. That is the key point here. And how this is connecting negative with positive. So once you choose your signs, and again, you could have done here negative, positive, and then here negative, positive, etc. But let's assume this is what we wanted, all of us. When you do your mesh analysis, you want to solve for the currents. There are two unknown currents, this one and this one, even though there are multiple loads. And there are two independent sources, this one and this one. So since we want to find the current, and there's only two of them, we know that we need two equations, one for current 1 and one for current 2. The way to build the equation is using Ohm's law for each mesh. So for instance, Z1 comes from this load, Z2 comes from this load, right here, the resistor, and Z3 comes from this capacitance. Okay, so obviously, if we have to write here, Z1 is going to be 0 real, and then plus 2 imaginary, because we're doing inductor. Z2 is equal to 4 real, 0 imaginary, because it's a resistor. And Z3 is going to be a capacitor, so 0 real, negative 1 imaginary. This is your impedance for each element. Now, when we build the equations, we have to follow the mesh rotation. So E1 is going from negative to positive, therefore E1 is positive. Then we find load 1, and it's going from positive to negative, so it's negative the current 1 times the load 1, yes, like so. And then we go to Z2, which is going positive negative, so it's negative, we're going to write down negative I1, which is current, because we're doing current 1 still, times Z2, so another negative. But remember that Z2 is connected to current 2, and that's how we're coupling both sides of the circuit. This load 2 is connecting both sides of the circuit and is letting us know which current is going to be dominant. But for E1, current 1, no, sorry, not E1, E1 is the load. For I1, the sign is going to be going negative, positive, because now we're talking about I1 contributing to Z2 with plus and negative 1, and then we're doing Z2 with contribution with I1, right? And if we notice, I2 is going positive, negative. Therefore, we have plus I2 Z2 equal to 0. So again, equation 1 goes this mesh, which is I1, Z1, Z2. But as we said, Z2 has contribution from I1 and I2. So when we write equation 1, we have to do the contribution of Z1, of I1 and I2. The contribution of I1 is negative because it's going positive, negative. The contribution of I2 is positive because since we're doing mesh 1, the polarity we choose for mesh 1 is first negative and then positive for I2. Okay, it's going like this in a circle. And it's first going negative positive, which this is what we designed. So that's why it's plus I2 Z2. For equation 2, we have a similar situation where if we start from Z2, we see, okay, but now we're going with this convention where I2 is going positive, negative, therefore it's negative I2 Z2, which is pretty much what we have too, negative I2 Z2. And then we have positive, negative, so it's negative I2 Z3, I2 Z3. And then we still have to do Z2 for the contribution of current 1. But notice that in this particular case, we're doing I1 with the polarity of this section. So it's going from negative to positive. So I1 is positive. So I1 times Z2 positive, which is right here. And the source, which our mesh is going positive, negative. So negative I2. Sorry, negative E2. So if you reorganize, remember that the independent source is going to be on the right-hand side to solve the equation easily. So we have, by just organizing terms, we have E1 and equal to E1, and then the second equation equals to E2. And then we combine terms for the independent terms, which is I1 is independent, I2 is independent. This should be I1 and I2, right? This is I1 from here. It's a typo there. Excellent. So if you remember, last time for DC circuits, we decided to do a system of equations where if you organize them like this for columns being I1, I2, and the independent source, then you can solve this using system of equations. You can solve this however you want. So go ahead and try to solve using Python or MATLAB, or see if Excel can save or solve it. See if you can do it by hand. But the point is that Z, the impedance, has an imaginary term. So be careful when you do the math. That's why I think you should practice using a calculator. Now, let's do another example. And this particular example is very similar, except for now we're saying this ladder network is going to be in series. This is going to be Z1, impedance 1, this guy. Now this is going to be Z2, and Z2 is very important because Z2 is connecting mesh 1 with mesh 2, and this by itself is going to be Z3. So notice there's only two currents, electric currents, therefore there's only two equations. And this is exactly the same. We choose the signs, so we're going to go here first, negative plus. Then we're going to say, in order to connect these to the loads, we do the negative plus, therefore it's going to be negative here, and it's going to be negative here. And then the second term is going to be negative plus, and then negative plus. So you go ahead and do however you need. This is negative and this is plus. Again, it's something that you do by convention, clockwise rotation, but the signs are however you want to compute them. And this is exactly the same as we did. In fact, here I'm showing you the equation already organized. And since the sources are combined, this part, you're going to have contributions of source 1 and source 2, where as before, we had independent contributions of E1 and E2 with each sources. But now we have a combined contribution of the first source and the second source. Notice that the first current, which is an unknown that we want to find, is Z1 plus Z2, and that obviously is because we had to reorganize terms. And if you notice, Z1 has a contribution of I1, Z2 has a contribution of I2. And then on the other hand, I2 has contribution of Z3 and Z2. So Z3, Z2. I would have to reorganize this on this part because we usually want this first column to be I1 and the second column to be I2. Once you have your equation, you can just go ahead and solve it. And this is the whole trick about mesh analysis. One difficult part for sure, where a lot of mistakes can happen, is solving the equation. So again, see if you can use Python or MATLAB or your calculator, because by hand it will take you a long time. And really, the focus of this chapter is to be able to build the system of equations correctly, and of course solve it, but you can always use the calculator if you want to solve it. Okay. A very important thing to mention is that these things, to be able to solve them, if you want to solve them in a calculator or by hand, they have to be in rectangular coordinates, meaning the real part plus minus the imaginary part. So this phasor notation has to be transferred to real and imaginary. How? We know how to do that. Z times cosine of theta and z times sine of theta for x and y. And as I said before, z equals x plus jy. Okay, so this is the value that you input here and here. And if you just say, the calculator will take that, the calculator has a little I on top. Some calculators even have the J. So you would simply type 4 times, or sorry, 4 plus 5 I times I. This is how you input in your calculator. I like using COMSOL, or sorry, not COMSOL, but MATLAB and Python, because you can write down the variable as complex variable beforehand, and you solve the equation. So please try to solve the equation because we'll have to practice this for homework. And of course, that's again, this is why you should use calculator or MATLAB, because if you have more than 2 electric currents that are unknown, then your system of equation is going to be bigger. In this particular case, we have 3 unknown electric currents, so we have to solve for a system of equation of 3 by 3. So if you look at this example, we have an independent source called E1, another independent source called E2, and then we have all these loads, passive loads, or passive elements. So if you notice, it can be simplified as this circuit on the right, where Z1 is R1 plus the reactance due to the inductor. So if in other words, Z1 is this top inductance, sorry, this top impedance. Then it's saying that Z2 is the contribution because of the resistor, and that is true. You cannot connect this resistor to these elements because they're in series plus parallel configuration. Then Z3 is going to be this one. We said Z3, yeah, Z3 is going to be this one, just to keep the same notation. And Z4 is going to be this one. So this one is going to be a very interesting case because if you notice, well, if you notice, let's go to this, sorry, if you go to this case on the right, the load due to impedance number 2 will have contributions of electric current 1 and electric current 2, right? The load, or sorry, the electric current 3 will, in this particular mesh, all of them are clockwise, rotating clockwise. And if you look at, if you look at impedance number 3, you have contribution of current number 2 and current number 3. And impedance load 4, you have contribution of current 1 and current 3. So in other words, the system of equation here would be for current 1, it's going to be the contribution of load impedance 2 and impedance 4, right? And that is true. For impedance 1, you have 2 and 4. And for, of course, actually, let's go ahead let's try to do the full equation, the first equation for mesh 1. So the first thing we know is going to be 3 unknowns because I1, I2, and I3 are unknowns. And there are 3 meshes. So we have 3 unknowns and 3 equations. Each equation is for a mesh. So current 1 is going through Z2 and Z4, which is true. This is correct. Z2 and Z4, and is negative plus, and we're saying this is negative plus, and we're saying this is negative plus. So then we're saying that I2 is going through Z2, and then this is, since we said this is plus, then I2 is going through here, so it's negative I2 times Z2. So this is true. And then we said that contribution because of load 4 also has contribution of I3, and since it's plus minus, then it's negative I3 Z4, right? And I1 is positive. The first equation does seem correct. Then the second case is very interesting because if you notice, current number 2 has elements contributing from this load, or from this mesh, and from this mesh, and obviously from this mesh. So I2 has contributions from Z1, which we can say this is negative positive. So it goes negative positive times Z1. Yes, this is true. Look at this case here. Then has contribution of positive, and so in this particular case will be negative positive on the top. So it has contribution of Z2. Yes, that is true. And has contribution on Z3. Yes, that is true. So this particular one has contribution from everyone. And then since Z2 is connecting to mesh 1, there's going to be contribution from mesh 1, and Z3 has contribution from current 3. And obviously the last one is going to be the contribution between these two, which is going to be, so if you see for mesh number 3, we have E2, right? And then we have E3 connecting Z3, which is right there, E3 connecting Z4, which is right there, and we have E3 connecting, or Z3 connecting to I2, and Z4 connecting to I1. Very well. So after you organize all the terms, you're gonna see that you have a diagonal term where the columns match Z1, Z2, Z3. So now we have 3 equations, 3 unknowns. And these will give you the current 1, the current 2, and current 3. Very well.